Hi everyone. Before we start, just wanted to let you know I have my window open today. It's kind of nice weather outside, so you may hear some cars passing by. Occasionally I may stop if it gets too loud, but otherwise hopefully it'll give some, I don't know, ambience for this video. But anyway, let's begin. So how do we graph polynomials and rational functions using calculus? This is actually a section where we'll put everything that we've learned so far together, and you'll see even some aspects from previous courses like intercepts. And so it's kind of a nice chapter to kind of review everything prior to the last couple of sections. So even the intercepts, if you'll notice, the y-intercept is the easy one. You can plug in x equals 0, and so for y, we'll always have a y-intercept unless we have an asymptote there. Pretty much majority of the time we'll have it. And then find x-intercepts. We can set equation equal to 0. Then you can either solve for x if possible. It may not be possible, unfortunately, sometimes with polynomials, especially higher degrees, if you cannot factor. Occasionally you may have to use technology, say graphing calculator, and you may have more than one x-intercept. So then we can use critical numbers or critical points that we can find with first derivative. If you recall, there was three kinds: stationary if derivative is 0, singular if derivative is not defined but original is defined, and maybe endpoints. And we can use first and second derivative test. Don't forget this step. You have to determine if your critical points are maximum or minimal to be able to classify them. And find points of inflection, pretty much following step 2, but with second derivative. You can set it equal to 0 and then put it on the number line with second derivative and look for change in concavity. And when it applies, behavior in your points where function is not defined. Typically this is only relevant if we have rational functions, for example, where we have vertical asymptotes. So polynomials pretty much are defined everywhere on the domain. And rational functions find vertical asymptotes. Let's say we have a vertical asymptote, x equals a. So what you need to do is check for the behavior from the left as x approaches the asymptote from the left, and as x approaches the asymptote from the right. They may not be the same, but typically the function is going to go to infinity or negative infinity. And I'll show you, you can do this analytically or by looking at the graph. So for example, if we have a function x plus 1 over x minus 1, and vertical asymptote, if you may note, the denominator is 0 when x equals 1. So this one I did analytically. Limit as x approaches 1 from the left is negative infinity. How did I know that? I picked, let's say, a point close to 1 but smaller than that. If you recall with limits, let's say 0.9, and the top would be positive, but 0.9 minus 1 would be negative. So a positive number divided by a small negative number will go to negative infinity. And as x approaches 1 from the right, let's check with 1.1. Now we're dividing positive by positive, so the function will go to positive infinity, as you can see. So I have it written like this. I think this is how you'll see it on the homework instead of the limits, but you can also do it with limits. And then behavior at infinity, if it applies, then we may have limits at infinity. Sometimes it's infinity or negative infinity, or sometimes it may be a value. So let's see how it applies with 3 examples from the homework. And of course, there's a portion to sketch a graph at the very end. But let's take a look at number 3 that we did in class, but let's quickly go over this. Let's say we have a function g of x equals to x cubed minus 12x, and we do have an interval from -4 to 4. We can find x and y intercepts. For y-intercept, plug in 0. You'll get 0 as the result. So that's 0, 0 is the y-intercept. For the x-intercept, but let's set the equation equal to 0. We cannot factor it completely, but we can do something. We can pull out an x. And then what I did is set each part equal to 0. I set x equal to 0, or x squared minus 12 equal to 0, which means x squared equals to 12. I think on the homework, it will accept answers with that you don't have to reduce. For example, positive radical 12 and negative radical 12 when you write out the points. But of course, you can also pull out 4, which becomes a 2 radical 3, and write it like this, just in case And it's, you can do it either way. And also we may get it as a decimal. What is radical 12? About 3.46. So we can graph it a little bit more accurately a little bit later. Now, how do we find any max or min? Let's find the derivative, which is 3x squared minus 12. To find stationary points, so let's set it equal to 0. And in this case, we can graph. You can pull out a 3. You'll have x squared minus 4 left, which factors as x minus 2 and x plus 2, for example. So I'm getting two values, x equals 2 and x equals negative 2, which are stationary points. We do have a couple of endpoints, negative 4 and 4. We don't have any singular points, so I didn't even note them. And so we have 4 critical points, which we can test as we're used to. Put them on the number line. So I used first derivative test mostly because there are endpoints. Because for second derivative, we can only test it for stationary points. So if you have endpoints, might as well draw it out. So this part is called the first derivative test, this number line that you guys see. So I plotted the endpoints, which I denoted with brackets. And then I put the two stationary points, negative 2 and 2. Typically, we need a test point between the two stationary points just to track the sign. So with the endpoints, we can just plug them into the derivative. I would specifically plug them into the factored version of the derivative. So let's say if I plug in negative 4, I'm getting negative in the first parentheses and negative in the last parentheses. So the product would be positive. So that means the function's increasing all the way up to negative 2. And we do have a minimum since we're increasing from that point. Then, if I plug in 0, our pick test point, and then we'll get negative times positive, which is negative. So the function's decreasing from negative 2 to 2. So we do have a maximum at negative 2. We can even visualize this. And we can plug in 4, and I get positive, and it's increasing, so we have a minimum at 2. But because at 4, it's a maximum because we're coming up to that point, and all the nearby points would be lower than that. And then I simply plugged in all the points into the original function. You can also put it into y equals 2 as if you were to graph it. You can check. You may want to do that anyway to compare your graph, and you can use the table to look at all these points. And sometimes that's easier to do. And so I'm getting negative 16 and positive 16, and so they're alternating between minimum and maximum. Okay, now on to inflection points. If we take derivative of the first derivative, which was, if I recall correctly, 3x squared minus 12, so we'll just get 6x. And we set that equal to 0. And which basically, if we divide by 6, we get x equals 0. We must plot that on the number line. So if you note, we can plug in negative 1 and 1 into the second derivative. For example, negative 1 plugged into 6x will get negative. And then if we plug in positive 1, we'll get positive 6. So that's positive. So the concavity does switch from negative to positive. And so 0, 0 is not only y-intercept and x-intercept, but it's also an inflection point. Sorry about all this noise. Occasionally I pause, but the street is really busy right now. Maybe I should record over the weekend next time. But anyway, moving on, behavior near the points where the function is not defined. Well, the function is defined everywhere in the domain because we have a polynomial. It's not a rational function. Behavior at infinity, we have endpoints, negative 4 and 4, so the function does not extend to infinity. So, and I basically plotted all the points, negative 4, negative 2, 2, and 4, and I kind of approximated the x-intercepts. Really, it should go through 0, 0. And then I approximated about negative 3.5 and 3.5. So that's the sketch of the graph. And another one I wanted to do is how do we use technology for x-intercepts. So there's one similar one like that on your homework. So here we have a polynomial with degree 3 that does not factor easily. So again, we can find y-intercept, just plug in 0 and you get 1, so it's 0, 1. And here's how I use graphing calculator to find x-intercepts. If you notice yourself getting lost on these steps, maybe look up some YouTube videos on using graphing calculators to find zeros or x-intercepts. You basically can search for it and maybe you'll come up with lots of options. But this is basically the steps that I follow. first plot the equation into y equals 2 as if you were to graph. You may want to do that anyway. Then click on graph. It's okay if you don't see the overall graph. You may be maybe max and min may be cut off depending on the window. But I typically use a regular window. If it's a little bit hard to see where the graph crosses x-axis, maybe you want to zoom in a little bit and change your x min, y min in the window. So play it by ear. I just use -10 to 10 for this graph, for this function. Then click on trace, basically so that you can be near that 0 or x-intercept that you're trying to find. Otherwise, it would just put you in the middle. I think for me it was just the middle by default every time, unless I move the trace ahead of time. So basically position the trace near that x-intercept. It can be, ideally, you should be to the left to begin with. That way you stay to the left of it. So then you would click on second trace. So you'll be in the calculate menu. And there's lots of options in it to that calculate menu. You will actually need option 2, so you can actually click on 2 or click enter. If you go down to 2, select it and then click enter. Then you'll see the left bound with a question mark. So what you want to do is position the cursor so it's slightly to the left. Sometimes it's above x-intercept, sometimes it's below, depending whether you're increasing or decreasing. So you may have to, play it, kind of eyeball it. And then you'll click enter once you position it to the left. So click enter. Then you'll see right bound with a question mark. Click the right arrow so you're a little bit to the right. And then again, click enter. And then the third one is guess, which I guess is just a guess point. I usually just click enter at that point, and finally you'll get the answer. So it may take a couple of tries, and then it gets a little bit quicker as you get used to it. And then you have to round it to the nearest 1 decimal place for homework. So this is what I got for this function. -3.30, about 0.10. Occasionally on your homework, it actually may be close to 0, so you may actually have to input. It might be 0.03, for example. So you may have to round it to 0. And the third one I got 1.8, 0. And then find max and min. So I took first derivative. I got 6x squared plus 6x minus 12 equal to 0. I factored out 6, and then you can further factor to get x plus 2 times x minus 1. So we have 2 stationary points. We did not have endpoints, if I recall, just stationary points. So you could have used second derivative here if you wanted to. In fact, we do find second derivative. But I just used first derivative just to get used to it. So I plotted -2 and 1 on the number line. Then I had to pick 3 test points, let's say -3, 0, and 2, to plug in into the factored version. And so I got maximum for -2. No, please note the typos. It's actually a max, and a minimum for 1. So again, try it with second derivative and see if you get the same result. Same thing for inflection points. Take second derivative, which is right here, 12x plus 6. And you can set it equal to 0 to look for inflection points. I got -12. So plotted on the number line once again now with second derivative. So I basically picked -1 and 0 to plug in. So if you plug in -1, you'll get -6 in the second derivative. So it'll be negative, concave down. And if you plug in 0, you'll get +6, which is up, concave up, positive. So -0.5 or -12, and 7.5. Again, I got this from table, or you can plug it in, but it is an inflection point. Now, once again, the function is defined everywhere. It's a polynomial, but we do have behavior at infinity. Basically, you can either look at the graph or look at the leading term, 2x cubed. So as x gets increasingly negative, if we're talking about large negative numbers, if you cube it, you'll still get negative number. Times +2, it'll still be a negative. So I have y approaches negative infinity as x approaches negative infinity. And vice versa, y approaches positive infinity as x approaches. So as x gets more positive, then you'll get a bigger positive number. So, and you can see it from the graph too. I just used Desmos to copy and paste the graph. This is what it looks like. Here is a max, here is a min. Conveniently, Desmos actually does show x-intercept and max and min. So if you're checking graph, you can use Desmos instead of Graph and Calculator. You're probably see a clearer picture, and you can zoom in and zoom out very easily. If you're doing it on a tablet, you can just do it with your fingers and it will zoom in and zoom out for you. And as you notice, it does go on to negative infinity on this end and positive infinity on this end, and so on. So this is what the graph looks like. That's it for that one. And sorry, I sped up a little bit. The last one is the rational function we actually did in class. There's another one on the homework which is similar. You have, I think it's x squared plus 1 over x squared or something like that. So for this one, we have t squared plus 1 over t squared minus 1. It's actually a little bit easier to find intercepts with rational function. Interestingly enough, this is one easy step. If you plug in 0, you'll get 1 over negative 1, which is just negative 1. And then for x-intercepts, you set the equation equal to 0, multiply both sides by denominator, which will cancel out on the left, and on the right is 0 times denominator, so you'll just get 0. So you'll get t squared plus 1 equal to 0, but that's not actually ever 0 because t squared does not equal to negative 1, not for real numbers, so we don't have x-intercepts. The graph does not cross the x-axis, which is good to keep in mind. We'll actually use that fact later. And then find max min. To find the derivative, this is actually practice of quotient rule. If you recall, it's derivative of the top times the original bottom minus derivative of the bottom, so they're both 2t, times original top, and divided by denominator squared. So once you distribute the 2t, notice the two leading terms, 2t cubed and negative 2t cubed, cancel out. And so you obtain negative 4t over t squared minus 1 squared. Once again, if you set it equal to 0, you can multiply by denominator. So we'll get negative 4t equals to 0. And so that means t equals to 0. So we have a stationary point here. We don't have singular points. If you recall, the original function has to be defined, but these are just asymptotes, so they do not qualify. They're not potential max or min. But we do have endpoints in this case. So I plotted all of them once again because we have endpoints, we have vertical asymptotes. I plotted everything on the number line. Why did I include vertical asymptotes since they're not critical points? Simply because the sign can change. What the function is doing on one side of the asymptote may be no guarantee that it's doing it on the other side, or it might be doing it in a different way, for example, as you'll see on the graph. Anyway, I plugged in negative 2 because the derivative is negative 4t divided by a square denominator. The denominator would always be positive, so I'm just looking at the sign in the numerator with a negative 4t. So negative 4t times negative 4 times negative 2, will get you positive. So function's increasing, so at the end point we have a minimum. Then on the other side of the asymptote we have 0. And then I try to pick negative 0.5 and 0.5 because we need some test points between the asymptote and the stationary point. So I picked negative 0.5 times negative 4. Once again, we get positive. So function's increasing once again. But on the other side, 0.5 times negative 4 would get us negative. And so the function is decreasing. So we have a max at 0. And at 2, once again we get negative times negative 4, so we have a minimum at that endpoint. So then I plugged in all three of them into the original function. So we get negative 2 5/3 and 2 5/3 are both minimum, but 0 negative 1 is the maximum. I think we've seen the graph of this one. Well, it'll become apparent shortly why is the maximum lower than minimums. This is a tricky part, taking second derivative of the rational functions. In this case, we would have to use chain rule and quotient rule, but do not let this scare you because it's still possible to do so. Let me kind of walk you through the process. So if you recall, derivative of negative 4t, because remember it was negative 4t over t squared minus 1 squared at the first derivative. So derivative of negative 4t is negative 4 times original bottom, which is t squared minus 1 squared. And then what's the derivative of the bottom? I paused the video and actually wrote the first derivative, so it's actually right in front of us. So once again, and then minus, let's use chain rule on the bottom. So the 2 would come down, so it's 2 times t squared minus 1 times the derivative of inside, which is 2t, times the original top, which is negative 4t. So again, sounds like a lot, but let's keep track of them. And the bottom would be square of a square, which is a fourth power. So I just cleaned this up a little bit. Basically, all I did was multiply the negative 2 times 2t. We'll get negative 4t times negative 4t. We'll get positive 16t squared. So everything else I left pretty much the same. Now, here's the trick that would simplify this a lot. If you pull out t squared minus 1 out of both these two parts and cancel it with the bottom, it makes it a lot easier to get the final answer. So if we pull out t squared minus 1 right here, notice I already canceled it with the bottom and make it a 3. So what do we have left? We have negative 4 times, notice how it's just 1 t squared minus 1 left, not squared anymore, and then plus 16t squared for the second term. And then all you have to do is distribute negative 4, so you'll get negative 4t squared plus 4 plus 16t squared, and then combine the t squareds, you'll get 12t squared plus 4 over t squared minus 1 cubed. So a lot of that work, but when you set it equal to 0, you do not get inflection points because 12t squared is 0 at the best, or positive, because of the square, and then plus 4, so you'll never get 0. It's never equals to 0. So there are no inflection points, which with rational functions is not a surprise. It's actually fairly common. However, it's still a good exercise to do because you can still test for concavity. You can plot asymptotes. You may have to do that for your assignments, but you can plot the asymptotes and look for the change in sign. So it's still a good exercise. And last, I guess, but not least, we do have two vertical asymptotes, negative 1 and 1. So we must check for the behavior around the asymptotes. For that, if you have the first derivative test done, let me actually pause the video and copy it for you guys. So I copied first derivative because it'll help us answer some of the questions. For example, as t approaches negative 1 from the left, the function's increasing, so you'll actually be able to tell it goes to positive infinity. In fact, if you start drawing the graph, with the asymptotes, and from negative 2, I think it's 5/3, because you have to go up from their point. It's increasing, and you also never cross the x-axis. So it's positive infinity. And now as t approaches negative 1 from the right, you'll have to kind of read this graph backwards. We know the graph is increasing, so it kind of looks like this, because we have a maximum at 0, negative 1, and then we have another asymptote. So you have to read it because the function is increasing from left to right, but it's actually going down from there. When you're at 0, negative 1, we know we do not cross x-axis, we cannot go up, and it's also, it would not be a maximum. So we know it goes to negative infinity. Now, what about as t approaches 1 from the left? That was actually fairly obvious because see how the arrow is going down, so it's negative infinity. Now what about 1 from the right? Again, you have to kind of read it backwards, but you can also draw it because I think the endpoint is the positive 5/3, and from here you can never cross x-axis, so you have to go up, and you can also read the graph because you have a minimum. So there's a couple of ways, and so it goes to positive infinity, or you can just look at the graph to really be able to tell which way it goes. So we have 4 limits, which you can rewrite as y approaches infinity or negative infinity. And here's what the graph looks like. And for part E, the function does not extend to infinity, so we don't have to do that part. And that's it for this video.